Let's get started. So, at the Jamboree, you already told us what you're going to talk about today. So, gravity waves in different backgrounds, something like this. So, please take it away.
Perfect. Thank you, everybody. So, who was not at the Jamboree last week? Maybe a show of hands for people at home, just to know how I should maybe balance myself. Oh, so I assume everybody was there. I'll repeat most of the things that I said anyway, just to keep it simple. I have a list of things I want to discuss here. And it turns out that the new work did not really fit during the seminar if I want it to be basic. I'll be mentioning the problems. And if people are interested anyway, if people want to know more, I'm always available. And I'll probably discuss some more during one of the cosmology meetings. So people who should be aware of it will be. Okay, so let me start to explain what I will be talking about, and it's gravitational waves in general relativity. And this is a very technical talk. Again, I'll try to explain all the steps quite in detail, but it's really trying to explain how we study the propagation of gravitational waves in general relativity with multiple levels of abstraction. Well, as you might know, Timmy's first gravitational wave model, and then go into something more complicated, we can call truly generic. So let me explain maybe gravitational, our current model of gravitation, which is general relativity. It's a relatively simple theory. Everybody laughs here. Everything is predicated on this object, G mu nu, which is a metric. For people who are not comfortable.
Omar, sorry for stealing your thunder, but would it be possible to move the mic a little bit towards your chest, or at least that's what MJ suggests? It's like it's still a little bit staticky and noisy for the virtual folks. Yeah, I'm not sure if that helps.
Better.
I think so. Yeah, go for it. All right, yeah.
Just speak less loud, maybe. Shouter, unfortunately. So of this object, which describes curvature of space-time in every point of space and time. This mu is just some time coordinates and some space coordinates. Can you see my hands pointing at things, JJ?
Yeah, I can see your hands, but the static issue is still going on. I'm not sure what the good solution is. Maybe MJ has a good suggestion, or?
Oh, maybe it's a mic?
Yeah, maybe you can switch the microphone to see whether it's better or not.
Yeah, maybe. Yeah, sorry.
No, this is growing pains. Hello? How's it going?
I think that might be better.
Might be better?
Yeah.
Okay. Let me know if the problem persists. Is it very distracting on a scale from 1 to 10?
It's like a 5, I guess.
Okay. I guess we'll survive a 5. It's too bad for the registration, I guess. So this is object with metric, and with a simple object, we built more complicated objects. We can build more complicated objects. These are the Riemann tensor. I will not write its definition because it's very complicated, but suffice to say that it's based on some double derivatives of the metric G. This is a very schematic way to indicate this. It contains terms which look like two derivatives of the metric. And the Riemann tensor is very, very important because it's related to observables. What the Riemann tensor encodes is the fact that if I am a vector, I don't know if the audience can see, but whatever. If I am a vector pointing in a specific direction, if I go forward and then left, I'll be pointing in a certain way. But if I go left and then forward, in flat space, I'm still pointing in the same direction. But in a curved space-time, that does not happen. So this Riemann tensor encodes this property of curved space. And so very important. You'll see it's very important also for gravitational waves, because the difference between the two polarizations of gravitational waves meaning that if I have some test particles in a circle and a GW passes by, the circle can move either by alternating these two kind of motions, so up and down, left and right, or the motion diagonally. This we call it plus and cross polarizations. And so you see from the little enactment of the vector, you might see how this Riemann tensor is also connected to these two different behaviors for the polarizations. By contracting the Riemann tensor, if you don't know what contracting means, this is Einstein's notation. The idea is that if you have repeated indices, so this is some vector v of rho. I repeated the rho twice. What I get out of this is some scalar. So I can build more complicated tensors by contracting the Riemann tensor, which is what we do all the time in GR. Very simple theory. Again, it's just, I don't know, it's misunderstood sometimes. That's how I feel about it. So we have a Ricci tensor and a Ricci scalar. Now, these objects, why do you need all of these contractions, Omar? What are you on about? Why are you talking about this? Well, it's because all of these combinations of the metric, remember the metric is the ultimate ingredient, create what we call Einstein's field equations. These equations, the term on the left, based on these tensors that I just defined, encodes curvature, encodes the metric. The term on the right is the energy content of the universe. So this tells you how, and you might have seen this, well, there must be some proportionality constant here, because the units are different, no other reason. This tells me, okay, if I have energy in the universe, I change the metric of the universe. So this is one direction of how metric can influence curvature. For the rest of this talk, we will kind of neglect this contribution, more or less. That is because the propagation of gravitational waves, it's usually studied on a curvature background. We don't care much about the presence of matter. Again, if you have questions about that, we can talk about it. This is a basic setup of GR. And now let's see how we can do gravitational waves in this setup. And I think I said this to the Jamboree. The idea is relatively simple. Oh, any questions? No? Okay. The idea is relatively simple. The metric is decomposed in a background and something which you might call a perturbation wave. When you impose this condition by saying alpha less. And you ask, the wave must be tiny compared to the background. It's a linear perturbation. This statement, I don't know. I'm not a big fan of this, and I'll explain why. But it could make sense in certain contexts. So let me put an asterisk on this. I'll get back to it. And then you plug these ansatz into your Einstein's equations, right? You linearize them, which means that your Einstein equation becomes two equations. And you might have seen this, like this is just a simple linearization process. Some background equation and some perturbation equation. So this contains everything that depends on the background. And this is just whatever depends. It can depend on H and G bar, maybe only on H. I don't know. How's it going, MJ? Is the audio fine? Okay. So we look at this. So you might want to care about the equation for the perturbations because it should be your wave equation. And through another step, which I put an asterisk on again, you find some wave equation. Ideally, this process should lead to something that looks like a wave equation. Box of H equals 0. This box of H is because a box. Can you see the box? Yeah, you can. This box is like some time derivative. spatial derivative squared, and so it's really a wave equation. The solution is symmetric under translations of t minus x, but doesn't matter. This is a wave equation. So we want to get to here.
Yeah.
Omar,
quick question.
Yeah.
So the metric equation box of h equals 0, does that only apply to flat spacetime?
Background can be anything. It doesn't have to be flat. Does that make sense?
Okay, I didn't know that.
So if you have, okay, so there's many ways to see this. In usual perturbation theory, for example, when you're interested in matter, you might plonk matter here and say the potentials created by matter are just a perturbation which I put in H. In my treatment now, everything that's not a wave ends up being G bar. Clear?
Yes.
Cool. Yeah. So now it's a moment for questions. This is end of one.
I think this is similar to what JJ was asking, but if you're not in flat space, does box just look different?
Yes.
Okay, so you
Good question.
yeah.
Yes, exactly. So the box, formal expression, it's this, where derivatives, I'm using nabla here. But in GR, they're not just derivatives over the space coordinates, they contain also something else, a connection, which makes it more fancy and curved. Yeah. So for example, for cosmology, here you would have something that accounts for the expansion of the universe. It's all in the box. It's all in the box. So we finished now with the first part of this talk, which was about like GR in a nutshell, and like explaining GR in 3 sentences and the gravitational wave simple model. Any other questions about this? I can answer any question about GR. And probably make mistakes. All right. So let's move on to the second part of this Blackboard seminar, which is talk about why this picture that I described here is simplistic and why we need to go deeper into what are these asterisks, why the smallness of H is not something simple to impose, and why going from Einstein's equations to this box is not just a matter of plugging things in, but it's something more conceptual. So I can cancel this. It'd be nice to save these somewhere, but let's see if I can do that. So Einstein's field equations, these are called. Is G mu nu equals 0 for us because that. I would like to keep it. I think it's it. Cool. All right. So GR is a very simple theory when you express it in its dynamical equations. It's one line, it's one symbol, maybe 2 symbols if you have matter. That's amazing, right? It's beautiful. This hides a freaking ton of complexity only through like this notation. As I told you, right? I explained you contract everything with everything, but it's like like we have included. This is 4 indices, right? For people who do programming, this is a NumPy array, which has 4 indices. All of them go from 0 to 4. So it's a very complex object. It's 4 times 4 times 4 times 4. Not tiny. And somehow remember, this is related to observables. So I have to unpack everything and go back here if I want to discuss observables. So not too easy. And this beauty and this complexity come together in the form of redundancy. GR can be expressed as simple because it's a very redundant theory. Not all of these objects are important. Not all of the elements inside these tensors are important, only some of them. Freedom, it's called gauge freedom. Gauge because if you want, it's like, I'll explain. We call it gauge freedom because it's based on a symmetry of a theory. And the symmetry is very simple. I should be able to change my coordinate system, my reference frame. So let's say I'm using x as reference, and then I move to x prime, and my laws should stay invariant. No other law of physics can do this. In classical mechanics, you write an equation which is valid in every inertial frame. GR completely generic. No matter how you define x, v, acceleration, jerk, whatever, it doesn't matter. You can have all of that. The equations are the same. There's an incredible beauty to that, right? Unfortunately, it comes with a downside that we have so many objects here and we don't need all of them. To explain exactly what this freedom entails, when you change coordinates, you end up changing the metric. So the object which was the basis of all of this changes because it's something geometrical, right? So it's not too surprising that if I change my grid, I change how I measure my curvature. This is how it changes. So this is a bit of a weird notation. So this is slightly new because it's similar to x. And this is a bit of a weird notation, but by this I mean so the metric changes. Let's see the first problem with this approach. When I do a coordinate change, if I split this G prime and G into my wave and background, so this is everything prime on the left, everything not prime on the right. You see that I've added something when I change reference frame, but now I don't know if I should consider that wave or background. So does this term change my definition of wave, or does it change my definition of background? I need something to impose this. And you might think that this condition is enough to say this is tiny, just say this term is tiny, so I just consider it a perturbation. And that's one way to approach it, but it's not enough. And I'll explain better more why that's not enough. And so this is the crux of this problem. Defining a wave means also defining a wave in every possible gauge that you're allowing. We really don't know how to do that. We have some examples, and I'll go through them later, which are in flat space and in the high frequency limit. But in a generic way, we still do not have a way. And this is what I was trying to accomplish with a colleague, and maybe did. There's still some caveats, but maybe we have reached this point. What's interesting here that I want to talk about is also the possibility that you might have a scalar field. You might know that if you define temperature on a point in space, the definition of temperature does not depend on how you define the grid in space, right? So scalar field is coordinate invariant, we said. And so a scalar field stays the same under gauge transformations. Now here we have a little bit of a problem, which is, well, the scalar field remains the same. If I define perturbations of a scalar field, those are not gauge invariant. And I'll explain why in a second. Perturbation. Okay. Where this is defined as just a derivative of a background field. Is clear more or less notation? Some derivative of a background field. So why do you get this term? Well, this perturbation is defined using some Taylor expansion on the point. The derivative appears when you do the Taylor expansion. That derivative depends on how you define your derivatives. And you need a reference system to define derivatives. So perturbations are not gauge invariant, which is a bit funky if you think about it, because they're still some form of scalar field. Unfortunately, they're special in GR. And so this is how things can change. While we call this covariance sometimes, the fact that GR does not depend on the reference system on your coordinate frame. Reference frame or coordinate system, sorry about that. This is also powerful because So remember here, I defined this h mu, which is a wave. And as I said during the Jamboree, some of you might remember, this h mu is a complicated object. It has 10 components. Something like this 3 here, and something like 9 here. This is a schematic. Please don't. It's not a matrix. Nine components which are like space. So imagine like running through these indices, and some spatial vector up here. This is 10 numbers. There's only 2 gravitational waves. Oh, I canceled it, but the plus and cross. And so we have 8 redundant components. How do we get rid of these components? Well, thank God we have all of this. Imagine I figured out a way to affect only the perturbations. So my econometric, I'll remove it from this transformation. Right? My change of coordinates only affects the perturbations. If I figure that out, now I can define a psi in a way that I can manipulate h before and after the transformation. So for example, I can define what we call gauge fixings. Traceless is one of them. So I say h does not have a trace. All of the elements of the trace sum together are 0. This h can define it. Another example, this is traceless. Another example of gauge fixing is what it's called the unitary gauge, which is used for field perturbations. Delta phi equals 0. Remember, because I can define xi such that delta phi prime is 0. Does that make sense? So it's just solving this equation, which in this case it's simple. This other case a little bit harder, but you can always do it. This is called unitary.
Omar, there's been a question if in the future you could write just a teeny bit larger, or yeah, it's cool. I mean, it's my job to monitor the chat. Don't worry.
I will write a bit larger. Yeah, sorry.
Yeah. No. Yeah. It's all good. I mean, this is all working in progress.
Clear?
Yeah, I think it might be just the bottom. Yeah, it's the video does a good job of resolving things, but it's still a little blurry at this scales. So
the zoom compression is not ideal for.
Yeah, sorry.
Blackboard, I'm afraid. It's okay.
It's all good. Yeah, we'll work through it. It's all good.
First trial.
Yeah, you're doing an awesome job. Thank you so much.
So this gauge transformation can be used to, so these gauge transformations can be used also to limit your complicated h mu and cancel some things, right? So it's powerful. It's a complexity. It seems boring, but in reality, it's extremely powerful. These gauge fixing are necessary. They are necessary because I can't keep spurious things in it. I want to distinguish what are my physical modes and what are what we call my gauge modes. Especially because the physical modes are what's observable. So what enters in the Riemann tensor is always the physical parts of H. Only I could try and do by keeping all of this junk and bringing it forward until I get a solution for this. Or I can say I simplify it at this level, and then I compute the observables with only 2 numbers. That makes it much easier. And so that's what we're trying to do here. All right, so any questions about this? This is about the gauge fixings. It's the second part of this Blackboard talk.
I'm sorry, just a question. Is this all just within the context of cosmological perturbation theory?
This is GR. So the statements I make, it's really about general relativity in general. Yeah. So
sorry, but the separation of G in G background plus H, if you do have like fully nonlinear equations, is way more complicated than just separating that.
Agreed. Yes, completely. So it's linearized theory. Yes, this is linearized GR.
Okay.
Is that better? This H does not contain Newtonian potentials. It only contains what I call a wave.
True, but okay, but
it's linearized. You're completely right. Yes.
It's linearized, but okay. Sorry if I go ahead in this, but Just a small comment. Is there a possibility of having like very large gauge modes growing in a simulation? If this is the way in which things are done?
So exactly, we want to avoid that.
Okay.
What I'm saying is that with the gauge freedom, you try and define. So you've written some equations which are valid in every reference frame. Then you use the trick and you say, I put myself in a frame where things look easier. You can always do that. And then you simplify your equations that way. I don't know in simulations how it's done, but it's possible that you actually just simulate everything. Then your gauge modes maybe go crazy and mess up everything. Here, that's why I think I'm trying to build this theoretical technology, which should give some guidance also for the expectation.
My question is, if in linearized gravity, that's still doable?
Yes, yes, exactly.
Okay,
Yes.
thank you.
Definitely this assumption of linearized, somehow we need to generalize this. H is tiny.
Okay.
We need to make it generic enough. And for that purpose, let's switch to the next section, which is gravitational waves in flat space. During Jamboree, I mentioned that, oh, lots of people have already talked about gravitational waves, Omar. Why do you think you're doing anything new? Again, why are you thinking about this problem? It's been around forever. Well, because most of the statements you've heard about gravitational waves come from the flat space solution. That's how most people teach them. That's how most GR books do it. Maybe you should switch to better GR books, perhaps, but it's, for example, some intro GR book like Sean Carroll talks only about gravitational waves in flat space. And now I'm not assuming that everybody's read Sean Carroll. That's not what I'm assuming at all, but it's just the intro view. So I want to write down here, and trace the stage, just to keep it. Hey, whee. Angry birds. I'm interested to know, yeah, what's the approach to all of this nonlinear theory? I'm not used to that. I guess there's people working on that, so that could be nice to discuss at some point. GWs in flat space. Is this clear more or less until now? Any points of? Sure. Cool. Flat space. In flat space, all of this discussion becomes so much easier, so much easier. That's why people like it a lot. It is a Minkowski metric, which is flat space, something like diagonal minus 1, 1, 1. It's a very simple form. Again, I put this squiggly line because you should never see a metric as a matrix. It's something more complex than that. Now I realize my eta and my h might be very similar, but this is eta, and this is h. And now you see, because eta only contains very simple expressions, which is just the number 1, we can always impose h mu nu, its amplitude, kinda, should be less than 1. Because I fix the background to a specific form, and I say I only consider reference frames where this is my background, I solve the gauge condition problem. I can only move in reference frames where the perturbation, so I take my full metric, I remove flat space, what I get out should be tiny. That's all. And so I limit myself in the number of gauge freedoms, but that's okay. Sometimes we don't want to write the laws of physics in every possible frame. And in this case, we keep it so that the perturbation stays linear. And this is one way to address the first asterisk, definition of H. Then there's the second asterisk, which is a complicated maths. And so let's take these ansatz. Let's plug it into our Einstein's field equations. We took, this is a metric, let's put it into Einstein's field equations. I'm not going to do it because, again, this is a long and tedious calculations. What you get is that the linearized, so the extra bit that depends on H equation has things which look like also kind of a Riemann tensor, some double derivatives of H. And these double derivatives come in many forms, unfortunately, because remember, I did not put any indices here. So this could mean, for example, a box of h mu nu or other things. So I'll write them down now, all of them. This can be this, but this can also be something like this, where I contract one derivative with one h. It doesn't matter if you're confused by exactly what these terms mean. What I'm trying to say here is that this form contains many terms. One, which is the one we like, box of h, and some more, which is the ones we don't like. How do we cancel them? Gauge freedom. For example, this contains a trace. And so I can say, oh, I go into the traceless gauge. And so poof, this cancels. I don't have to care about these terms in delta G. And there's another term, which is this one. And to cancel this, we have to go into what is called the Lorentz gauge. You might have heard in electromagnetism. It's to impose that it's a little bit complicated. Your wave, okay, assume you have a wave solution to it. The plane, the wave is, what is that called? Not coplanar. Oh my God, it's transverse. So the direction of propagation of the plane where you see the wave are perpendicular to each other. And so here, Lorentz gauge, to cancel this, traceless, cancel this. Traceless means h equals 0, one condition. Lorentz is 4 conditions. We need to impose 3 more conditions. Remember, we have 8 redundant modes. And we started with 10. 10 minus 2 is 8. We need 8 conditions to impose. The additional condition which is imposed, it's called spatial. It doesn't matter. It's something that tells you, like, my gravitational wave affects space. It's not boosted in any complicated wave. It moves only through time. Spatial. And so I hate when people study gravitational waves and they say, oh, we're going to the TT gauge, transverse traceless. Yes, okay, you're going to the TT gauge, but you need more. But you've got to tell me what else do you do. And this spatial condition is very important. You can't always neglect it, like people do. Only it's somewhat trivial, so people just, whatever, forget about it, I guess. And so I did this second step, which I put an asterisk on. I need to do the complicated maths, it's conceptual. I figured out what I need, how I can exploit my gauge freedom. And the magic actually comes out in flat space. You get box of h equals 0. You get a nice, beautiful wave. This is great. We figured out waves, Omar, right? Oh, we have figured out very little, because when you do all of this gauge fixing, you can't just do what you want, even if by the looks of it, I did what I wanted. You need to make sure that what you're doing never goes against the dynamical equation. So I could impose that my wave is not transversal. So this transverse gauge, instead of imposing this, I can impose something similar, maybe longitudinal. Can I do that? No, because that really goes against my dynamical equations. And so I need to keep that in mind. That always needs to be kept in mind. And so when you go to generic spacetimes, some of these conditions are a little bit iffy unless you define them properly, which is what I'll be talking about next. If there are any questions about gravitational waves in flat space, this is the time. Can anybody read this? Should I actually write much, much larger? No? Oh, there's more questions?
Yeah, I think that's okay.
Oh.
If anyone else disagrees, though, feel free to either put a note in the chat, or speak up.
Okay, cool. So we have these gravitational waves in generic spacetimes. How do we make this thing that we talked about in flat space, generalize it to something which, where here I do not have to have flat space-time. This is a little bit more of a complicated question. As I said during the Jamboree, Isaacson in '68 has tried to approach it first, and now it has becoming, people are more interested in it because we're actually seeing gravitational waves, I guess. Before, everybody was happy with Isaacson. I think we can still improve it quite substantially. And so let's go through this generalization. What's the deal? Well, when we do this decomposition, I said, when you write this down and you impose that your metric, your wave is tiny compared to the metric, to the background metric. Let me call this alpha. I said it's hard to do the split. But one of the problems is that the definition of tiny, while in the metric itself could depend only on the amplitude of h, when you go into your dynamical equations, because they depend on derivatives of h, you need to make statements also about its derivatives, so that you get a handle of it. You're not just linearizing G, you want to end up with a linearized Einstein equation. And so you need to satisfy the split in every equation that you're writing, right? Because it will be possible to have a tiny quantity here, but then becomes dominant here. And so I can do the split at the level of G, but I cannot do the split at the level of big G. Might be a little bit confusing, but so this is another equation compared to this. So I need to maintain the split, so I need to make statements about the variation scale of h, which is what we do. So the variation scale, I write it very schematically. Some derivative of h over h, which will bring down on 1 over r, where r is a typical wavelength. Let me call it lambda, in fact. Then I do the same with the background. Also have to impose epsilon. And these two conditions here, which are called the smallness condition. My perturbations must be small, and the fast varying condition. My wavelengths must be tiny compared to the background wavelength. Again, I need this in theory because I have these weird objects in my equations, which depend on derivatives of h, so I need to control also its derivatives. So we impose these two conditions, and it turns out that then you're restricting yourself to certain reference systems where these conditions are maintained, right? I can move around with my gauge freedom, but in order to build a consistent framework, I cannot move too much away from this. And so what we can do is explore how this affects this gauge parameter. Do you remember, like x goes to right here, maybe x prime is x plus psi. What we do is that we say, okay, this must satisfy both the smallness and the fast varying condition. And I will not go through the derivation maybe, but I mean, it's very simple. But you can see that by looking at the gauge transformations, maintaining this implies, we can see it maybe. Oh, that's fine. If I say this effect only should be of the same order of this, I'm saying the derivatives of psi should be of order alpha, because that's the amplitude of this h. Then by integrating this in the sense that if I think of the derivatives that bringing down a factor 1 over epsilon, I also get that the smallness implies these two conditions. So psi should be of order alpha times epsilon. Again, because an integration really brings up a factor epsilon, you can think of it in terms of exponentials. It doesn't matter. It's not a strict definition. It's very end wavy, and there's no lying in this. Like, people accept this. You must verify that this is satisfied once you plug in your configuration, but that's about it. So small and fast varying. Any problems about this? Why do we need this split and how we implement it? Okay, so this is a view of gravitational waves in generic spacetimes as of today. It turns out you need to do another check. And the check is that we have verified that, well, I told you that somebody has verified that this split is consistent. The split of the field equations is consistent. You need to do this also in the observables, because that's really what you care about. And ideally, if you have this and this, you would also have the observables, but it's not a given. And so to check this, this is what we do. Is it epsilon and alpha can be used as a smallness parameter to define some expansion. Right, they're tiny. I said they must be tiny. So h mu, I expand it.
Actually, you might, Omar, do you mind if I ask a quick question about this smallness parameter separation?
Yeah, yeah.
So is this separation of different length scales equivalent to, okay, sorry, there was an interruption. Is this separation of length scales equivalent to saying that your space-time is always at least locally flat?
Exactly. So
Okay.
this fast varying, yes. So the wave only sees flat space locally. It can never be coupled to any curvature. It can never feel any curvature. You're effectively neglecting any of these weird tensors I've defined. They never enter an H, a leading order. That's really the main problem of this, actually. More importantly, these two smallness parameters actually have a hierarchy.
Well, I think so. I don't know if it was them or Dave's massage, but things just started to take that.
Cool. So the smallness parameters have a hierarchy. Epsilon must be smaller than alpha. You can ask me where that comes from. And so that's why I'm expanding in epsilon, which is like this small parameter. Very, very risky. So my gauge parameter is psi mu with my coordinate transformation also is expanded. But as you might see, I said psi must be of order epsilon. So I see that my condition implies that I'm losing the zeroth order. The leading order does not exist. That's nice. And then let's talk about the observables. And now there's going to be a twist in all of this, which maybe nobody expected until now. But because epsilon is tiny, I can go into negative exponents of the power. So actually, this is a perturbation of a Riemann tensor. So the part of a Riemann tensor that depends on H, right? Again, I linearize things. I have things that depend on G bar and things that depend on H. The part of the observable that depends on the gravitational wave, which is what I care about if I want to see gravitational waves, actually has a leading order 1 over epsilon squared. And then there's a 1 over epsilon. Then you would have the 1. And so let's say I have all of this situation. Every time you do an expansion, you need to truncate it at some point and verify that your equations are consistent, but you're not missing terms from another higher expansion order that enters your, for example, observable. And so you might say, I just take the leading orders. Is that enough? It turns out yes. This
Sorry.
is fully yeah.
Just a question. That power of 1 over epsilon squared or 1 over epsilon does not mean that you're introducing a different choice in either space or time coordinate, because you can actually do a reinterpretation of parameters such that you can absorb the epsilon dependence and go back to your original consistency condition.
You're right. So
yeah.
you could define some conformal transformation here, right? That's what you're telling me about.
I would say that you can, instead of doing singular perturbation theory, that you can do regular perturbation theory by just doing a coordinate redefinition. That's something that people normally do.
Yeah, I don't think you will get a different result.
Mm-hmm.
We can talk about it. Yeah.
Okay.
I like this idea because, yeah, you define some smallest parameter when you try and use it, but you're right.
Mind if I also ask a question? Sorry.
Yeah.
When epsilon goes to 0, does that present any problems with how you expand the Riemann tensor?
Very well, very well, very well. So epsilon goes to 0, recovers our flat space solution. So it's true, it's not, you have something that's divergent, but we know the solution in that case. And you can see that the limit is smooth. So you're connecting to it in a proper way.
So in the limit.
Sorry, John, but that's why I was mentioning that if you do a coordinate redefinition, you can you are able to do it. You're able to do again the limit epsilon going to 0 and go back to flat space-time solution, because that can only be done by just coordinate reabsorbing finding a proper time or a proper space where h can become small with respect to your background metric. So you can just.
So remember, the idea of all of this is that I haven't said what is space and what is time. All of these derivatives are very hand wavy. I know if I had some coordinate system, I could definitely do that. I want to try and keep it generic, even if I lose some formality in how I define these smallness parameters. I see how the two are, interchangeable. All right, this is a final thought. It turns out that this whole expansion is actually very powerful because your observables, not only this is consistent, but you also get that this order is consistent. And this is, no matter how many terms you grab here, you have to grab, like you need to enhance also the orders in psi and h, but then you can grab the observables also at this level 1 over epsilon. However, you can't go higher, and that's not because you can't keep eating terms here, but that is because this term is not gauge invariant. It turns out that all of these gauge transformations, while they work very well for h, while they work reasonably well for derivatives of h, because this delta r contains a double derivative of h, that means that you cannot take any possible orders in delta Riemann tensor. So my observables are somehow limited in how many effects I'm including them. And of course you say, oh, but this is third order. Why would you care about the third order? Well, because maybe I wanted to relax my assumptions of epsilon and treat it just as some parameter for the expansion and then set it to 1. If this calculation worked, maybe I could have thought about that approach to solving this problem. But you can't, because you realize things are not gauge invariant. That theory is not consistent. So sorry, bye-bye problem. In fact, this is problem number 1 with all this epsilon stuff. In fact, there's a problem 0, which is the fact that I limited my wavelengths. Problem 0. Hopefully there's no problem -1. So we have problem 0, we have problem 1. And then there's another problem which I want to talk about now. I think I have 5 more minutes. Okay, no, that's good. The final problem is related to the scalar fields. I talked about scalar fields. I think why did I waste our time understanding what's a scalar field if it's not needed so far? It turns out it's needed for what we wanted to do, which is study scalar waves. Now, let's try and do this also with a scalar field. So how does the expansion look for the scalar field? Well, it looks the same. So we have a 0th order, and we have a 1st order, then we have some more junk. To see which orders are consistent with what, here in a small parenthesis. So remember, the perturbations changed according to this law that contains our parameter psi. and some background quantity. Because psi is of order epsilon, I need to impose that my wave is actually tiny. It's also of order epsilon. Otherwise, every time I do, sorry, let me phrase it this way. My wave must also contain terms of order epsilon. Otherwise, every time I do a gauge transformation, I'm adding something of order epsilon to it. So if I were to keep only the leading order, I could never do any gauge transformation. Let me try and explain that again. This psi mu, I said the leading order is of order epsilon. So every time I do a gauge transformation, I add to my delta phi something which is of order epsilon. So if I want to be consistent, my expansion needs to keep track of the 0th order, but also the 1st order. To be consistent again, because my gauge transformations could introduce this, and I need to keep track of it. Unfortunately, this somehow escaped the entire field of scalar waves so far, and everybody neglects this. Everybody says, oh, we don't care about that, which is fine. You can gauge things away. You can set it to 0. Unfortunately, and this is problem number 3, setting delta phi 1 to 0 through gauge transformations means that you cannot impose the Lorentz gauge anymore. So your gravitational waves cannot be transverse anymore. And that's a bit funky because we know that gravitational waves affect things along their propagation direction in the plane. Sorry, gravitational waves affect things perpendicular to their plane of propagation. And somehow you lose that when you try and impose this condition. GWs, H mu, or not. Transverse. Again, this is quite the problem. We would like to have transverse waves. And one of the things that we tried to resolve was actually addressing this problem. It turns out you need to find gauge conditions which are not just the same in flat space. You need to generalize them a little bit. That's what we've done. I will not go into the details of what gauge conditions we do, but this is just to explain what is the problem with these high frequency things and why can't we just take the result in flat space and map a one-to-one what we have done in what we can do in a generic spacetime. These are my main 3 problems. Sorry, did I miss problem 2? I have problem 0, 1, and 2, not 3.
Yeah.
Skip my indices. And that's about it. Any questions, comment things, please let me know. I can explain things more in detail if people are interested as well. Thank you.
Thanks a lot. Things going online. I can't see the chat or the Zoom session. Questions? No questions? All right, so let's thank Omar again.
Thank you.
By Sarah, so I'll be announcing that by the end of the week. All right, there you go.
Thanks, Omar.
Thanks.